This is a recast of the 7,100-word piece, Federated Learning, from Schneeppet.com. This article is about federated learning, a decentralized approach to machine learning that addresses data privacy, security, and scalability concerns. It discusses the different techniques used in federated learning, the advantages and challenges, and its potential impact on various industries. Let's listen in.
Today we're diving into the world of machine learning techniques and exploring a relatively new approach called federated learning. Now, machine learning is a subset of artificial intelligence that allows computers to learn and make decisions without explicit programming. It uses algorithms to analyze large amounts of data and extract patterns and insights, which can then be used to make predictions or decisions.
That's right, Theo, and the really cool thing about machine learning is that computers can improve and adapt their performance through experience. They learn from examples and adjust their parameters accordingly. There are three main categories of machine learning: supervised learning, unsupervised learning, and reinforcement learning.
In supervised learning, the model is trained using labeled data where the desired output is known. It's like teaching a computer by showing it examples and telling it what the correct answer is. On the other hand, unsupervised learning deals with finding patterns and relationships in unlabeled data. The computer learns to detect similarities or clusters within the data without any prior knowledge of what it should be looking for.
And then there's reinforcement learning, where the model learns by interacting with an environment and receiving feedback in the form of rewards or punishments. It's like training a dog to perform specific tricks by rewarding good behavior and punishing bad behavior.
Exactly, Ben. Now let's talk about federated learning, which is the focus of this article. Federated learning is a decentralized approach to machine learning that addresses challenges in data privacy, security, and scalability. In traditional centralized approaches, all the data is collected and stored in one location, which can raise concerns about privacy and security.
That's where federated learning comes in. With federated learning, the learning process is decentralized and models are trained locally on devices while preserving data privacy. Each participant in the federated learning system trains a local model using their own data, and these local models are then aggregated to create a global model that combines the knowledge learned from each participant.
This approach allows for the benefits of machine learning without compromising user data privacy. It's a win-win situation. Participants can contribute to the global model without sharing their raw data, and the global model gets better and more accurate with each participant's contribution.
Absolutely, Theo, and the potential applications of federated learning are vast. It can be applied to various industries such as finance, healthcare, manufacturing, and transportation. In the financial industry, for example, machine learning algorithms can analyze vast amounts of financial data to detect fraud or make investment predictions.
And in healthcare, federated learning can analyze patient data to provide personalized treatment plans and predict disease outcomes. It's really exciting to think about how this approach can revolutionize these industries by automating complex decision-making processes and enabling data-driven insights.
I couldn't agree more, Theo. The implementation of machine learning techniques, specifically federated learning, has already resulted in increased efficiency, accuracy, and innovation across different industries. It's really transforming the way things are done.
Absolutely. But as with any new technology, there are challenges that need to be addressed. Federated learning requires coordination and communication between participants, which can be complex and time-consuming. And there are also concerns about the quality and representativeness of the local models contributed by each participant.
That's right, Theo, and scalability is another challenge. As the volume of data increases exponentially, federated learning systems need to be able to handle large amounts of data efficiently. It's definitely something that researchers and practitioners in the field need to work on.
Well said, Ben. The potential benefits of federated learning are immense, but it's important to overcome these challenges to fully harness its power. Understanding this emerging technique is crucial for anyone interested in machine learning and ensuring the privacy and security of user data.
Absolutely, Theo. Federated learning has the potential to revolutionize the machine learning landscape and pave the way for even more advanced technologies in the future.
That's right, Ben. So let's start by explaining what federated learning is. It is a machine learning technique that aims to train models on decentralized data sources while preserving data privacy. In traditional machine learning approaches, data is collected and centralized at a central server, where the machine learning model is trained. However, this centralized approach raises privacy concerns, as personal and sensitive data may be exposed.
That's where federated learning comes in. It leverages the distributed nature of data to train models locally on edge devices, such as smartphones or IoT devices. These edge devices learn from their locally stored data without the need to send it to a central server. Instead, only the model updates, encrypted using privacy-preserving algorithms, are transmitted to the central server, where they are aggregated and integrated into a global model. This ensures that the sensitive data remains on the edge device, protecting user privacy.
Exactly. And one of the key advantages of federated learning is that it allows the model to learn from a large and diverse set of data distributed across multiple devices without the need to send the data to a central server. This addresses concerns regarding data privacy and security, which are especially important in domains like healthcare, finance, and smart homes.
Additionally, federated learning enables collaborative model training, where different devices contribute their knowledge to improve the model collectively. This collaborative approach can lead to more accurate and robust models as compared to traditional centralized learning methods.
Absolutely. But it's important to note that federated learning also faces challenges that need further research and development to be fully exploited in practical applications. Some of these challenges include communication efficiency, model aggregation, and heterogeneity across devices. And in the financial sector, organizations dealing with finance, such as banks or insurance companies, can employ machine learning algorithms to gain insights from their customer data while maintaining data privacy and complying with regulatory requirements.
That's right. And in the telecommunications industry, federated learning enables telecom companies to leverage their vast amounts of user data to improve network performance and optimize customer experiences in the era of 5G and Internet of Things devices.
Overall, the implementation of federated learning spans across various industries, indicating its capacity to address privacy concerns and enhance collaboration in data-driven domains.
Absolutely, Theo. And looking towards the future, there are several potential areas where federated learning can be implemented. For example, in healthcare research and personalized medicine, federated learning can enable collaborative research without compromising patient privacy, leading to effective disease detection, improved treatment strategies, and personalized health recommendations.
That's a great point. And in the financial sector, federated learning can be valuable for detecting fraudulent activities and improving customer experience by collectively training machine learning models on scattered customer data across different institutions.
And federated learning can also be deployed in smart cities and Internet of Things networks to analyze data collected from different sensors and devices, enabling better resource management and urban planning.
Absolutely, Ben. These potential future applications showcase the versatility of federated learning and its potential to revolutionize various domains.
In conclusion, federated learning is an emerging technique in the field of machine learning that enables collaborative model training across multiple decentralized devices while preserving data privacy. It addresses the challenges posed by traditional centralized training methods and offers benefits such as reduced communication costs, improved model personalization, and continuous learning capabilities.
That's right. However, there are still challenges that need to be addressed, such as communication constraints, data and device heterogeneity, and security vulnerabilities. Future research efforts should focus on overcoming these challenges to make federated learning more practical and secure for real-world applications.
Absolutely, Theo. Federated learning holds great promise in revolutionizing the field of machine learning by enabling collaborative training on distributed data sources while preserving privacy. It offers a powerful solution to address privacy concerns, enhance performance, and foster a collaborative learning environment. Communication efficiency is a challenge because the model updates need to be transmitted from each device to the central server during the training process. This can be costly in terms of network bandwidth and latency.
Model aggregation is another challenge. Since each device trains a local model on its specific data, the central server needs to aggregate the updates from all the devices to create a global model. This aggregation process needs to ensure that the global model accurately represents the knowledge from all the devices while still protecting the privacy of individual device data.
And there's also the challenge of heterogeneity across devices. Each device may have different capabilities, such as processing power or memory capacity, which can affect the performance and efficiency of the training process.
That's true. Overcoming these challenges will require further research and development in areas such as communication protocols, privacy-preserving algorithms, and device heterogeneity management.
Absolutely. But despite these challenges, federated learning presents a promising solution for privacy-aware and distributed machine learning. It offers benefits such as reduced communication costs and improved data privacy, making it suitable for scenarios where data cannot be easily transferred or shared due to legal, regulatory, or privacy constraints.
And let's not forget that federated learning also enables automatic data labeling, as devices can label their data locally. This further reduces the need for data exchange and ensures privacy while improving the efficiency of the labeling process.
Yes, that's an important point, Theo. Federated learning has the potential to transform how we approach machine learning by allowing us to train models on local client devices while preserving data privacy. This opens up new possibilities for industries and applications where privacy and security are of utmost importance.
Absolutely. So if you're interested in machine learning or concerned about data privacy, federated learning is definitely something to keep an eye on. It's an exciting development in the field that has the potential to reshape how we train models and handle sensitive data.
Well said, Theo.
One of the main advantages of federated learning is its ability to maintain data privacy and confidentiality. With federated learning, data remains on the user's devices and only model updates are sent to the centralized server. This decentralized approach ensures that sensitive user data does not need to be transferred to a central location, mitigating privacy concerns.
That's right, Theo. By keeping the data on users' devices, federated learning allows for the training of models using large-scale datasets present across multiple devices. This means that models can take advantage of the diverse and distributed data available on these devices, potentially yielding better and more robust models.
Absolutely. And another advantage of federated learning is that it enables collaborative learning in scenarios where data cannot be shared due to legal, privacy, or security constraints. This is important in industries such as healthcare or finance, where sensitive data needs to be protected.
Definitely, Theo. However, it's important to note that there are some disadvantages to federated learning as well. One major drawback is the potential for a slower training process, since model updates need to be individually computed on each device before aggregation. This can lead to longer training times compared to traditional centralized approaches.
That's a good point, Ben. Additionally, federated learning requires a reliable and stable network connection. Without a good connection, the communication overhead may become a significant bottleneck and hinder the training process.
And let's not forget about security concerns. When models' weights are shared with clients during federated learning, there is a risk of reverse engineering attacks. This means that malicious actors could potentially access and exploit the model's sensitive information.
Absolutely, security is a major concern. However, despite these challenges, federated learning shows great promise in overcoming the limitations of traditional centralized approaches. It enables data privacy protection, reduces communication and computational costs, and allows for continuous learning and adaptation to local data.
That's right, Theo. Federated learning has already been successfully applied in various domains, including healthcare, finance, and the Internet of Things, IoT. It has the potential to revolutionize the field of machine learning by enabling collaborative and privacy-preserving model training on large scale.
And in terms of the architecture and workflow of federated learning, there are several key components that play a crucial role. First, we have the model owner, who coordinates the entire learning process and defines the global model that needs to be trained.
That's correct. The participants, also known as clients or edge devices, possess local datasets and perform the model training on their respective devices. These participants are usually mobile devices like smartphones or wearables connected to the Internet.
Exactly. The training process occurs locally on these devices, with the participants only sharing updates with the model owner. To ensure privacy and security, participants employ techniques like differential privacy or encryption during model updates.
And then we have federated optimization algorithms, such as federated averaging, that are adopted to aggregate the local model updates and generate a global model. This global model is then distributed back to the participants, and the entire process is iterated to refine the model over successive rounds.
This architecture and workflow of federated learning enable collaboration among distributed devices, ensuring privacy-preserving and efficient model training.
Absolutely, Theo. And to wrap it up, federated learning is a promising machine learning technique that offers advantages such as data privacy protection, collaboration in scenarios where data can't be shared, and the ability to work with large-scale distributed datasets.
However, there are challenges that need to be addressed, such as heterogeneity of edge devices, performance variations, and model inconsistencies. And of course, data security and privacy concerns need to be carefully managed to ensure user trust and compliance with regulations.
Indeed, Theo, as federated learning continues to evolve, it has the potential to revolutionize the field of machine learning by enabling collaborative and privacy-preserving model training on a large scale.
Absolutely. And one of the key aspects of federated learning is the workflow involved. Let's break it down step by step. First, the server initializes a global model based on a pre-trained model. This serves as the starting point for the collaborative training process.
Once the global model is initialized, it is sent to all participating devices in the network. These devices then train the model on their local datasets using their own computation resources. It's important to note that during this training process, the devices only send model updates, gradients, to the server instead of sending raw data. This ensures privacy and security.
That's right. The server then collects and aggregates the model updates from all devices to create a new global model. This aggregation step is crucial as it allows a global model to benefit from the knowledge of all participating devices. Additionally, a subset of devices can be selected based on their update quality or other criteria to further enhance the model's performance.
Exactly. These selected devices then retrain the global model by exchanging model updates iteratively. This iterative process continues until the model converges or a predefined stopping criterion is met. Once the training is complete, the server presents the federated model, which has been learned on the decentralized devices, and this model can be used to make predictions on new data instances.
And overall, this workflow allows for collaborative model training while preserving data privacy and minimizing the need for data transfer. It's an innovative approach that takes advantage of distributed data sources without compromising security.
Absolutely. Now let's delve deeper into the roles of different components in federated learning. The client devices, which are the primary source of data, play a crucial role in participating in the local training process. They not only train locally on their own data, but also share model updates with the central server for aggregation.
The central server, on the other hand, acts as a coordinator. It collects and aggregates the updates from various clients, using a specific aggregation algorithm to merge the models and generate a global model. This global model is then sent back to the clients for future local training.
That's right. The central server may also perform additional tasks, such as selecting clients for participation and setting up the initial model. The collaborative efforts of the client devices and the central server are essential in ensuring effective federated learning by utilizing distributed data while maintaining privacy and security.
Absolutely, Ben. Federated learning addresses the challenges of data privacy and security by only sharing model updates instead of raw data. It allows users to participate in the training process without sacrificing their data privacy. This approach mitigates the risks associated with data breaches and unauthorized access.
However, as with any technology, there are challenges to overcome. Communication constraints between devices and the need for decentralized computation can impact training efficiency and performance. Additionally, the heterogeneity of devices and data sources pose further complexities.
That's true. But despite these challenges, federated learning shows great promise in various domains such as healthcare, Internet of Things, IoT, and edge computing. With advancements in algorithms, communication protocols, and security mechanisms, federated learning is poised to become a critical component of future machine learning systems.
Absolutely, Theo. Techniques and algorithms in federated learning focus on optimizing model accuracy, preserving privacy, and ensuring efficient collaboration among distributed devices. Aggregation techniques such as averaging or weighted averaging are used to combine updates from multiple devices into a global model.
And dealing with device heterogeneity is another important aspect. Algorithms need to be developed that can handle variations in device capabilities, such as different computational capacities or network connectivity. Privacy-preserving techniques like differential privacy, secure multi-party computation, and homomorphic encryption play a crucial role in protecting user data.
That's a great summary, Theo. Federated learning is undoubtedly a powerful machine learning technique that enables collaborative and privacy-preserving model training. It has the potential to revolutionize the field by addressing data privacy concerns while still allowing for effective model training using distributed data sources.
Absolutely, Ben. It's an exciting field with a lot of potential. And with advancements in technology, federated learning will continue to evolve and become an integral part of future machine learning systems. One of the main points discussed in the article is the different techniques used in federated learning. One such technique is the federated averaging approach. In this technique, each client device trains its local model using its own data and sends only the model updates to the central server. The server then aggregates these updates to create a global model. This approach allows for efficient coordination and communication between the clients and the server.
Another technique mentioned is cross-silo federated learning, which overcomes data sharing restrictions between different organizations. In this approach, multiple organizations collaborate to train a shared model by exchanging model updates instead of sharing raw data. This technique ensures privacy and addresses concerns associated with sharing sensitive data.
And let's not forget about hierarchical federated learning. This technique is suitable for large-scale scenarios where multiple layers of servers and clients exist. It enables hierarchical communication between these layers, allowing for efficient coordination and communication. This approach is particularly useful in scenarios with complex network structures.
Privacy and security are critical concerns in federated learning, and secure federated learning aims to address them. This technique uses encryption techniques and secure aggregation protocols to protect sensitive data from unauthorized access. By employing these various techniques, federated learning offers flexibility and adaptability to suit different scenarios and requirements.
Absolutely, Ben. These different techniques provide a wide range of options for implementing federated learning in various settings. Each technique has its own strengths and weaknesses, and choosing the right one depends on factors like data sharing restrictions, network structure, and privacy concerns.
Another important point discussed in the article is the use of differential privacy techniques in federated learning algorithms. Differential privacy ensures the privacy of participants by analyzing aggregated data instead of individual data points. It adds noise to the data to prevent specific individuals from being identified through their contributions.
However, the added noise affects the accuracy of the model. To address this issue, researchers have proposed solutions such as the use of noisy gradients or differentially private aggregation techniques. These advancements in federated learning algorithms have shown great potential in overcoming the challenges of privacy and data heterogeneity.
Absolutely, Theo. These advancements in federated learning algorithms are crucial for optimizing the performance and efficiency of the framework. Choosing the right algorithm can greatly impact the stability, convergence speed, and accuracy of the learned model.
And to effectively evaluate these algorithms, metrics like convergence rate, communication overhead, privacy leakage, and model accuracy need to be considered. Future research should focus on developing and benchmarking new algorithms specifically designed for federated learning scenarios, considering the unique challenges and constraints imposed by the distributed nature of the framework.
That's right, Theo. Effective comparison and evaluation of various algorithms in federated learning are crucial for maximizing its potential. The distributed nature of federated learning makes choosing the right algorithm essential for achieving optimal performance and accuracy.
Absolutely, Ben. And as we discussed, federated learning has tremendous potential in various application domains such as healthcare, finance, and IoT systems. By addressing privacy concerns and reducing communication and computational costs, it opens up new possibilities for collaborative model training without compromising sensitive data.
However, federated learning also faces its fair share of challenges. One significant challenge lies in the security and privacy concerns associated with sharing data across multiple entities. Robust security measures are imperative to prevent leakages or unauthorized access to sensitive information.
Another challenge is the heterogeneity of devices and data sources in a federated learning setting. Different devices may have varying computation capabilities, network connections, and data distributions. Designing efficient aggregation strategies that can handle such heterogeneity and maintain data integrity proves to be complex but necessary.
Additionally, the communication overhead during the training process can lead to high bandwidth consumption. Minimizing the amount of data transferred while maintaining model accuracy becomes crucial in addressing this challenge.
And let's not forget about non-IID data distribution, where each device's data may not represent the underlying population distribution. This creates statistical bias and complicates the learning process. Adaptive aggregation and differential privacy techniques are being explored to overcome these challenges and enable successful federated learning implementation.
Absolutely, Theo. Despite these challenges, federated learning continues to evolve and improve. With further research and advancements in algorithms, federated learning has the potential to revolutionize machine learning and empower collaborative model training on distributed data.
That's right, Ben. And one of the main concerns in federated learning is privacy and security. Since multiple parties are involved in the learning process, the risk of data breaches and leakage increases. This is especially concerning when dealing with sensitive information like personal health records or financial data.
Exactly, Theo. The data remains on the local device, which means it can be exposed to external threats. And on top of that, the aggregation of models also poses a security risk. Adversarial attacks can be launched to manipulate the aggregated model by injecting malicious data into the training process. This can compromise the privacy of other participants and allow malicious participants to extract valuable information.
To address these concerns, various privacy-preserving techniques have been proposed. One such technique is differential privacy, which aims to protect the data and models from unauthorized access. Another technique is secure multi-party computation, which ensures that participants' privacy is maintained throughout the federated learning process.
Absolutely, Theo. These techniques are crucial in minimizing privacy and security risks in federated learning. However, further research and development in this area are still needed to enhance privacy protection and mitigate security threats.
Moving on to another challenge in federated learning, communication and bandwidth issues are significant factors to consider. Since federated learning requires exchanging models and updates between the central server and multiple participant devices, communication becomes critical.
That's right, Theo. The communication overhead can be substantial, especially if the models have a large number of parameters or if the participant devices have limited bandwidth. And it becomes even more challenging when participant devices are mobile or have intermittent connectivity.
Exactly, Ben. The heterogeneity among participant devices further complicates the communication process. Different devices may have variations in their processing power or network connectivity, which can affect the efficiency of communication.
To overcome these challenges, various techniques have been proposed. One approach is to use model compression techniques to reduce the model size before transmission, thereby reducing the communication burden. Another approach is to schedule the communication more efficiently, considering the bandwidth availability of the participant devices.
Additionally, leveraging the concept of differential privacy can ensure the protection of sensitive data while still enabling effective communication in federated learning systems. By incorporating privacy-preserving techniques, the communication can be streamlined while maintaining data security.
Absolutely, Theo. Mitigating communication and bandwidth issues is crucial for the successful deployment of federated learning in various real-world applications.
Now let's talk about some solutions and approaches to overcoming the challenges in federated learning. One solution is to improve the communication and coordination among participating devices. This can be achieved by employing advanced encryption techniques to ensure privacy and security while transmitting data between devices.
That's right, Theo. Another solution is to implement efficient data compression algorithms to reduce the amount of data that needs to be transmitted. This helps in reducing bandwidth requirements and improving communication efficiency.
And let's not forget about incorporating advanced machine learning techniques that can handle non-IID data, where the data on different devices is not identically and independently distributed. Personalized federated learning, for example, adapts the model to individual devices' data patterns, resulting in better performance.
Absolutely, Theo. It's also crucial to develop reliable and accurate mechanisms for device and model selection. By ensuring that the most suitable devices are selected for collaboration and that the models used for training are effective, we can significantly enhance the overall federated learning system.
Now let's take a step back and talk about federated learning itself. It's a decentralized learning approach that allows multiple devices or organizations to collaboratively train a machine learning model without sharing their raw data.
That's right, Theo. Federated learning addresses the limitations of traditional centralized machine learning techniques, such as privacy concerns and data security risks. Each device or organization trains the model using its local data and only shares the model updates with a central server, which are then aggregated to improve the model's performance.
And this collaborative learning paradigm has a wide range of applications, including healthcare, finance, and Internet of Things, IoT, devices. In healthcare, for example, federated learning allows healthcare institutions to train robust models using distributed data from multiple hospitals while ensuring patient privacy.
Absolutely, Theo. Federated learning also has significant potential in the field of IoT devices. With the proliferation of smart devices, federated learning can process data locally on these devices, reducing the reliance on cloud computation and preserving user privacy.
And let's not forget about other sectors like finance, cybersecurity, and smart cities, where data privacy and efficient collaboration are crucial. Federated learning presents a remarkable opportunity for various domains to leverage the power of machine learning while preserving data privacy.
That's right, Theo. One of the key advantages of federated learning is its ability to address privacy concerns by keeping data distributed and local. This means that sensitive data doesn't need to be transferred to a central server for training, reducing the risk of data breaches.
Absolutely. And this decentralized approach also allows for improved model personalization. Since training occurs locally on each device, the models can capture individual user behaviors and preferences, resulting in personalized recommendations and a better user experience.
And another benefit of federated learning is its ability to overcome communication constraints. With most of the data processing happening locally on the devices, there's less reliance on high-bandwidth communication, making it suitable for resource-constrained environments.
That's correct. And what's really interesting is that federated learning also enables continuous learning capabilities even in offline settings. By leveraging local computational power, the trained models can be updated and refined whenever the device reconnects to the network, ensuring up-to-date and efficient learning.
Absolutely, Theo. These benefits and outcomes have been observed in real-world scenarios across various industries. For example, in healthcare, federated learning allows hospitals and research institutions to collaborate on developing robust algorithms without sharing sensitive patient data.